Hello and welcome to Lecture 2 of Charge Separation and Storage in Phys 1204. There's a lot of fundamental physics that we can learn from thinking about capacitors, and on top of that, although it's probably not clear to you why yet, capacitors are also extremely useful practical devices. So we've looked at capacitors a bit, but now it's time to start looking at them in much more detail. We saw in the previous video lecture that any system of two charged objects can be used to store electric potential energy. Remember that if you think of a system of a plastic rod and wool that you rub and separate, then you do work on them, and as a result electric potential energy is stored in the rod and wool system. Or, in an alternative way of viewing it, that electric potential energy is stored in the E field surrounding the rod and the wool. In a circuit, rubbing things just isn't practical, so let's look at a more practical situation for storing potential energy using a capacitor. So we start with an uncharged capacitor, and because the plates are uncharged, it would take zero work to move a charge from one to the other, and so the potential difference between the plates is zero. And we're now going to connect them to a battery. Remember what a battery does. It maintains a constant EMF, and when it's just sitting there doing nothing, the potential difference between its terminals is the same as that EMF. So now we connect it to the capacitor with wires, and immediately charge starts to flow. A complicated flow of charge happens inside the battery, but in the wires it's much simpler. It's just electrons. Electrons are pulled off of one plate of the capacitor, they're pulled into the positive terminal of the battery, pushed out the negative terminal of the battery, and onto the other plate, which becomes negative. Throughout this, chemical reactions keep supplying charge to the terminals, keeping the EMF fixed, and as long as the flow of charge through the battery is slow enough, the potential difference across the battery terminals remains equal to the EMF. This is what a battery does in practice. It maintains a constant potential difference. Notice that the wires and the plates are not in electrostatic equilibrium during this process. Charges are moving around. We'll talk much more about that in the next unit of the course. Eventually, as the potential difference between the plates increases, we eventually get a situation that the potential difference across the capacitor plates is just the negative of the potential difference across the battery terminals. So think of it in terms of the ski hill analogy. If you were a skier getting on the lift at the negative terminal of the battery, you go up some potential difference to get to the positive terminal. You have to come back down the exact same potential difference to get back to where you started. We say the capacitor is charging when a flow of electrons is occurring and the charge on the plates is increasing, and we say that it's fully charged once that flow stops. Notice how this whole process is really a lot like the process of you rubbing the plastic rod with the wool to bring about charge separation. Again, work has been done on the system, where this time we're thinking of the plates of the capacitor as our system, and that's resulted in a change in potential energy. But now it's the battery that did the work. We've stored electric potential energy in the capacitor plates, or alternatively we can think of it as that we've stored that electric potential energy in the electric field between the capacitor plates. So it's certainly true that capacitors store potential energy. You'll often see it stated in textbooks and elsewhere that capacitors store charge. And while this is true, it's a misleading statement if you don't think about exactly what it means. Because notice that whatever the charge is on the positive plate, the charge on the negative plate is always of exactly the same magnitude. And so a fully charged capacitor has a charge in it of exactly zero. So the sense in which it stores charge is that separation of charge occurs and the positive and negative are stored on opposite plates. So perhaps we should say that a capacitor stores separated charge. Now I'm going to show you a little bit of a puzzle. I'm going to use the same setup that you've already used in the lab to sample charge on the plate of a capacitor. And this capacitor is hooked up just like you did in lab so that there's a 3000 volt potential difference between the plates. First, I'm going to take a reading on how much charge is on the capacitor with nothing in it. Then I'm going to insert some paper in between the plates and take the reading again. And notice that there is more charge on the capacitor when the paper is between the plates. So, first I sampled with nothing in between the plates, and I found a certain amount of charge. Then I sampled with paper between the plates, and what I clearly found was that there was more charge on the plates when there was paper between them. Note, they were still connected to the same power source. There was still a 3000 volt potential difference between the plates in both cases. Well, much of the rest of this unit is going to be spent on understanding this observation. Why is there more charge on the plates when we put something in between them? We need to start thinking about what happens when we change conditions for a capacitor. What happens when we change the plate size? What happens when we change the separation between the plates? What happens when we put something in between the plates? But there are two very distinct situations that we can have that we need to pay attention to the differences between. On the one hand, we can have the plates connected to a battery. In this case, what we've already seen is that whatever the potential is, say at this point A, as you pass through the battery, there is a rise in the potential by an amount equal to the EMF. There's no E field in the battery if there's no charge moving in it, right? It's in electrostatic equilibrium, so there's zero E field there, and so the potential is constant. And so the same has to be true of the other piece of wire over here between D and A, but we know we have to get back to the same potential by the time we get back to A. And so there must be a potential drop in the capacitor, which is the same size as the potential rise in the battery. The key thing to realize is that since the battery provides a constant potential difference, any time a capacitor is connected to a battery, the potential difference across the capacitor is fixed. On the other hand, if we've charged the capacitor and then disconnected it from the battery, now the plates are isolated, electrically isolated. And so, like any isolated objects, they can't exchange charge with their environment. And so in this case now, the charge on the plates is fixed. It's really important when you're thinking about changing conditions in a capacitor to keep in mind what's fixed. So let's look at the isolated plates case. Remember that what is fixed here is the charge on the plates. So let's think about what happens. Well, we know that increasing the plate separation is going to have absolutely no effect on the charge, because by definition the charges are fixed on the isolated plates. What about the E field inside? Well, we know that for a parallel plate capacitor, as long as the distance between the plates is small compared to the plate size, the E field is just proportional to the surface charge density. Well, we haven't changed the area of the plates, and the charge on the plates is fixed, and so there's no change to the E field magnitude inside the capacitor. Finally, what about the potential difference between the plates? Well, we saw in the last unit that the E field inside the plates is just the potential difference between the plates divided by the plate separation. Aha! Well, here we see changes. The E field, we already know, is staying the same. But S has increased, and so if the E field stays the same even though S has increased, that tells us that the potential difference between the plates must have also increased. Contrast that with what happens if you increase the plate separation while the capacitor is connected to a battery. Note, the plates are not isolated. Charge can go on and off of them. So I really should now talk about an initial and final amount of charge, because what's now fixed is the potential difference across the capacitor. Well, so again, what happens? We know that the potential difference is fixed, but we've just increased S. And so, since the potential difference is fixed and S increased, the electric field strength must have decreased. Well, we know that the electric field strength is proportional to the charge density, and if the charge density decreased, then the charge must have decreased. Note what that means happened. It means that as we pulled the plates apart, charge flowed back off of the plates through the battery, which means we must have lost some potential energy that we had stored in the capacitor. I'm going to leave it to you, partly during the questions following these lectures, to think about other cases. For connected batteries or isolated batteries, what happens when we change the potential difference of the battery? What happens when we change the plate area? What other changes can you come up with? So let's return to this question of what happens when we insert something inside the capacitor. Now, what I inserted was paper, which is an insulator, but let's start by thinking about putting a conductor, like a metal slab, in between the plates. That's going to turn out to be a little easier. One thing we know is that in this case, with the plates connected to a battery, the potential difference between the plates is fixed. And we also know from the previous unit that the potential as a function of position between the plates is just a straight line, and its slope is the E field. So now we insert this metal plate. One thing we know is that the E field is 0 inside that metal. And that's because negative charge collects on one plate and positive charge collects on the other. It polarizes. And that exactly cancels the E field due to the external influences so that the E field is 0 inside the plate. And so somewhere in here where that metal slab is, because the E field is 0, that means the potential is 0. However, we're still connected to the battery, and so the potential difference across the whole capacitor has to be exactly the same as it was before. And so that means there must be two sections here where the potential rises. And note that we now have to go up the same delta V, but we have to go up it in only these two distances instead of the whole distance S. These slopes must be larger. And so the E field must be stronger in these regions that don't have the metal in them than it was before we inserted that metal slab. And we know what that means because the E field in the capacitor is proportional to the charge density. And so the charge density on the plates must have increased as we inserted the metal slab. And that tells us that charge must have flowed. More electrons must have been pulled off the positive plate and pushed onto the negative ones, which means the battery did more work, and we've stored more potential energy in the system. The potential energy of the system increased as a result of inserting this metal slab between the plates. Well, let's have a question so you can see how you're understanding. So let's do exactly the same thing, but with isolated plates. I'll give you some hints. You know that the charge on the plates is fixed. Also, you actually know that the charges on the metal slab have to be the same as the charges on the plate. I'll leave you to think about how we know that that must be true. And so now you think about whether the potential difference between the two plates increases, decreases, or stays the same.